Hey guys, I'm here back in another math video. Today we're going to be doing Bay Area Math Olympiad 2015 number 3. I also took this BAMO and I did very bad on it, and this was one of the questions I could not solve, which isn't saying much. So try to solve it if you can, pause the video if you need to, and without further ado, I'll go on to the solution. So to start out, first instinct is to probably try out some values for k. So we can make a table here. K and xk, yk. And we will probably make a table, just put the first few values in. See if we can find a pattern or something. So I came up with this table, and I was doing it, and this is about as far as I got. I could not see a single pattern in this table when I did this question. I was completely stuck, and I could not go on. Well, it's hard, because after this step, you have to realize that because x is squared and y is squared, that x can be negative and y can be negative. You can just negate any of these values, make it negative, and it'll still be true. So actually, if you edit the table a little, you can actually see a pattern, which you just have to look for. You just have to know what to look for. There's no real way to see this pattern, but if we make the table like this instead, let's see, this also works, but now there's a pattern, and try to see if you can figure the pattern out. It's actually that if we have the table like this, we see that xk plus 1 is actually equal to xk minus 2yk, which is interesting. So as you can see, this value 1 here is just negative 1 minus negative 2 times negative 1, which is plus 2, so negative 1 plus 2, which is 1, and yk is yk plus 1 is equal to xk plus yk. A bit simpler. Negative 2 is negative 1 plus negative 1. Negative 1 is 1 minus 2. 4 is 5 minus 1. 11 is 7 plus 4. And so on. And this pattern seems to work as you go down. And let's see why this is. Let's just try to plug this in here. So let's square both of them. Plus 2yk plus 1 squared. This is what the expression they gave us is. And let's see if we can find a reason for why this works. Is equal to x. It's xk minus 2yk squared. That's just x squared minus 4xk yk plus 4yk squared plus 2 xk squared plus 2 xk yk plus yk squared is equal to 3 xk squared plus 2 yk squared. If, whoops, made a mistake there. If you simplify it down and such, and then that's very interesting actually. Oh, still made a mistake. Because that shows that, and from here we can use induction to prove the theorem. So if xk squared plus 2 yk squared equals 3 to the k, then if we substitute that into the equation, xk plus 1 squared plus 2yk plus 1 squared is equal to 3 times 3k is equal to 3 to the k plus 1. So thus, if this is true, then if we increment k by 1, this is true as well. So by induction, we can keep incrementing k. It's true. I think it's a theorem. I don't know. It's true by induction. We're not actually done yet. We proved that it's always true, but we also have to prove that neither of them is divisible by 3. We can't miss that. So let's try prove neither of them is divisible by 3. Let's use mod. So x1 is equal to -1, right? -1, so -1 mod 3. And y1, sorry, it's actually 3 horizontal, -1 mod 3. So xk plus 1 is -1 mod 3 minus 2, 2 -1 mod 3. So x2, as you can see, is 1 mod 3. And y3 is -1 mod 3 plus -1 mod 3, -2 mod 3, which is just 1 mod 3, as you can see. And we keep going. So x3 is, if we look at, we can just look at the table, or we can keep deducing from the equation. So 1 minus 2 is -1 mod 3. And y3 is -1 plus 1, which is 2, which is also -1 mod 3. And as you can see, this sort of goes down and keeps going, alternating between -1 mod 3 and 1 mod 3, never quite reaching mod 3. And thus, by this logic, neither of them is divisible by 3 either. So we prove the entire thing. Times 1 plus y squared plus 1 plus x squared divided by square root 1 plus y squared plus 1 plus x squared. My handwriting is getting progressively worse.